I do believe we're live. There we go. I am the king. So this stream is for mostly my tutor group who are a little bit behind. Hi Jack. Who are a little bit behind, and we need to go over topic 1 fairly quickly so they can use this as a reference as we go along. I've lost my drawing screen, which is there. So what I really wanted to do was to be able to view the chat in my phone. We'll see how that goes, shall we? And check my emails, because people are emailing me because I emailed everybody. Let's go back to here. It's just me and you, Jack, like the good old days. Think it'll be in YouTube? Think it'll be in Creator Studio? Oh, there we go. Live. I think I'll turn the sound out. How can he be looking at you in his sleep? Do do do. Oh. Hang on a second. Chat. Excellent. Oh, 3 people are watching. Can I see who's watching? I can't remember. It's been a while. 11 months, people were telling me the other day. 11 months. Whew, since I last uploaded anything. Crazy. Oh, I've got a whole new page for analytics. Stream okay, 5 concurrent viewers. Wow, look at this. Right, I'll tell you what we'll do. I don't seem to be able to see who's watching, so if you want to say hello, do so in chat. Your poor cat, all this snow everywhere, it's a bit icy. I've just taken the dog out. Right, let's have a look. We're going to start with Morgan, my dude. Right, let's start with a blue. Is that a blue pen? Oh, it's all set up for me. I want it slightly bigger. Pen. So let's start with the atom. So I think our model of the atom should probably look something like this. And we've got positive things, we've got neutral things, and then around the outside, not to scale, we've got negative things. So making atoms on a whole neutral. Got 2 plus, 2 negative, cancels out to make 0 charge altogether. So in this bit here, this is the nucleus, and you've done all this at GCSE, but it makes sense to go over it again. And here we have electrons, and inside the nucleus, we have protons, and we have neutrons. And it says that you need to know the simple model of the atom, which looks like this. We're doing it in this way with shells, because we need to talk about shells later. Shells will come into the quantum part of this topic, and we'll do energy levels in atoms. So we need to talk about the relative charge and mass, and the SI charge and mass. So in terms of relative charges and masses. Protons have a charge +1 and a mass +1. Neutrons, crimson mothriel. Hi Arthur. The size of a nucleus compared to a whole atom is a football compared to a stadium. Woo, go nuclear physics. Yeah, there's a great TED video about this. So neutrons have a charge of 0 and a mass of +1, and then electrons, that I can't spell, have a charge of -1 and the mass is about 1/2000, and we'll stick with that for now. So all of these masses are relative to the mass of a proton. So a proton mass in SI units is, maybe if I go over here, I can run out of space. Proton mass in SI units is, let's go mass of a proton, 1.67 times 10 to the power -27 kilograms. So in your data book it puts a bracket 3 in there, and the reason it puts a bracket 3 in there is actually the mass of the neutron is almost the same, 1.67 bracket 5 times 10 to the -27 kilograms. So neutrons are slightly heavier than protons, and that's good because then they can decay via beta decay into electrons. The mass of our electrons is much smaller, is 9.11 times 10 to the power -31 kilograms. So electrons are really teeny tiny in terms of their mass compared to the other particles in the atom. If we were to talk about charge is Q. The charge of a proton is 1.60 times 10 to the power -19 coulombs. That's elementary charge. There's nothing with less charge than that, or at least nothing that exists on its own. We'll talk a little bit about other charges, fractional charges, later. And then the charge in an electron is minus 1.60 times 10 to the power -19 coulombs. And we call that E, well, the magnitude of that is E, that's elementary charge. So elementary charge is the same as the magnitude of the charge on an electron and the charge on a proton. So we've done the charge and the mass of the proton, neutron, and the electron in SI units. So this is the mass of the proton, neutron, electron in SI units, and the charge on the proton and the electron in SI units, and then relative charges and masses. Charge for protons +1, electron -1, mass +1 for a proton, +1 for a neutron, and 1/2000 for an electron. The atomic mass unit, we'll use that in A level in the second year, but for Jack there, U is 1.661 times 10 to the power -27 kilograms, and that's something like the mass of a nucleon when it's inside a nucleus. So all that stuff is more or less recovered from GCSE. The specific charge is new, and I feel like we need more space for this, but it's okay. So specific charge is charge over mass. So the particle with the largest specific charge is the electron, and the units are coulombs per kilogram. Just going to open up the data booklet just to check which things you get and which things you don't. So use that as them in E equals mc squared. No, in E equals mc squared you use their actual rest mass. It kind of depends on the question. but you tend to use their actual rest mass in E equals mc squared. In the first year you won't need to use E equals mc squared, but in the second year you will. You also get, in addition to the mass in kilograms, you also get, well, you get the specific charge of an electron given in the data book. So the specific charge of the electron in the data book is 1.76. So if we go down here, say the specific charge of an electron is, I can't remember, 1.76 times 10 to the 11 coulombs per kilogram. I'll just double check that. Does anything happen when I do that? 1.76 times 10 to the power 11. You can't see that on my screen, can you? If we were calculating the specific charge of a proton, we do 1.60 times 10 to the power minus 19 divided by 1.67 probably times 10 to the power minus 27. That gives you the specific charge of a proton in the same way that we did for an electron, which would be 1.60 times 10 to the power minus 19 divided by 9.11 times 10 to the power minus 31. Of nuclei and ions, so if I had a nucleus, I'm going to have to rub some things out now. Oh, I've rubbed out my little sign, look at that. If I had a nucleus, then I'd have 1.60 times 10 to the power minus 19 multiplied by the number of protons. Now the number of protons is called Z. And then underneath that, for the mass, we'd have 1.661 times 10 to the power minus 27 multiplied by A, and that's the mass number. So we've got Z, which is our proton number, and A, which is our mass number. So we've got the mass, the magnitude of the charge of each of the protons multiplied by together, and then divide all of that. We can put brackets around this. I don't think we need them. Bid mass, yeah, we probably do. And then we've got the magnitude of the mass of each of the nucleons multiplied by the number of nucleons, and that will give you a total specific charge of a nuclei. If it's an ion, then the charge is going to be different and the mass might be different depending on the size of the atom. If you always use the electrons, you can't go wrong, so we'll do it like that. So for an ion, you'd have 1.60 times 10 to the power minus 19 multiplied by the charge on the ion all over. Now this time you'd have U, which is 1.661, multiplied by A, which is our mass number, plus the mass of the electron times by the number of electrons. Really only makes a difference if you've got lots of electrons, but you need your total charge of the ion, which is a charge on the ion times the elementary charge, all over the mass of the nucleus of the ion plus the mass of the electrons in the ion, and that will give you your specific charge of an ion. And the specific charge of a nucleus would be the charge of all the protons, all divided by the charge of all of the nucleons. So it says you should be familiar with proton number Z, nucleon number A, and nuclide notation. We're going to use this notation here. So if I rub this one out, whoop, and we use this notation, and X is our element, A is our mass number, and Z is our proton number. So that's our mass number, X is our element, and Z is our proton number. If we do nuclear decays later, we can use the same notation but change some of the symbols. So if our element changes to Y, say we've got, if we have a beta decay, we get an additional proton, and then we get the same number of nucleons. So we've got element X changes to element Y via beta decay, and the proton number goes up, but the mass number doesn't change because a neutron decays into a proton. The meanings of isotope and use of isotopic data. So when we had our nucleus that I drew earlier, oh, hang on a second. I forgot that I could rub out those things. I thought I could just rub out things I drawn. So if we've got our isotopes, then in the nucleus we had earlier, we had 2 protons, 2 neutrons. That would actually be He, 4 nucleons, and then 2 protons. So A would be 4, Z would be 2, and N, that would be the number of neutrons. N equals the total mass number minus the proton number. If we've got an isotope, then we might have 2 protons, but 1, 2, 3 neutrons. So we've got the same element, He, all elements of the same type have the same proton number, and then we've got 5 this time for our mass number. So isotopes is a definition that comes up quite regularly. Isotopes are elements with the same number of protons but different numbers of neutrons. So helium-4 and helium-5 might both be isotopes of helium. In use of isotopic data, you may well be given things like this, asked to figure out the number of neutrons, asked to figure out the specific charge of a nucleus. Interestingly, this one is also called an alpha particle. So a helium nucleus is an alpha particle when we've got no electrons whizzing around. So alpha particles have a charge of +2, same as a helium nucleus would. If you've got any questions, pop them in chat and let me know. I can see I've got 10 people watching. This may well be the largest number of people watching ever. Excellent. But I still can't figure out how to see who's watching. Oh well. All messages are visible. Ooh, participants. There you go. Oh, just me. You're all hidden. Holy Pig Frill. What a name. What a name. Right, we'll move on to the second section. Oh, thanks Reese, that's very kind. And a kiss as well, gracious me. Gracious me. I should say don't forget to smash the like button, although I've got no idea what difference that would make to anything. I'm being attacked by the dog. Right, let's clear this screen up a bit. Move on to stable and unstable nuclei, because this is where it gets a little bit weird. Because we need to start talking about the strong nuclear force. What is it, dog? What is it? Come here. You got a little bed. Come and lie down. being attacked by the dog. I thought it was about 20. Jack knows. Jack's an OG stream participant. Right, strong nuclear force is a bit of a weird one, because if we do a graph of... Oh, can I do straight lines? Yes. Excellent. Bam, bam, bam. See, I'm remembering stuff. If we do a graph of force against distance, so the magnitude of a strong force against distance, positive forces are repulsive, negative forces are attractive. For our strong force, below 0.5 femtometers, we have a very, very repulsive region. So things don't want to be in the same place. Very short range repulsion, closer than 0.5 femtometers. So on this graph, 0.5 femtometers is where the force crosses the axis. Any closer than that, so if we have two nucleons closer than that, then they repel and they come back over to here. If we have a radius between two nucleons of 3 femtometers, then there's no effect. So it's no effect from the strong force after 3 femtometers. So it drops away to 0. And femto is times 10 to the power minus 15, and then it's in meters. Actually, femto is not anything to do with meters, but we're working in femtometers. That is the strong force. So the strong force is holding things together, and in our nucleus, our electrostatic force is pushing things apart. So the protons are pushing each other apart, but the neutrons and the protons are all holding each other together. So all nucleons hold each other together if they're within this area here. So if they're between 3 femtometers and 0.5 femtometers, then the strong force is attracting nucleons together. This is for baryons, so protons and neutrons. If we have a distance greater than 3 femtometers, then the electrostatic force can win. And if the electrostatic force wins, then bad things happen. Radioactive decay. So if we think about a larger nucleus, I'm not going to draw all the bits. If I think about a proton over here and a proton over here, then everything surrounding this proton is pulling it into the nucleus. It's by the strong force. Everything surrounding this proton is pulling it in. But if we have a much greater separation, and by much greater, let's say 10 to the power for a nucleus, well, say it's something like 10 femtometers, so they're separated by 10 to the minus 14 meters, then the electrostatic force is pushing these away from each other, and the strong nuclear force past 3 femtometers has no effect. Ooh, Joe is a new subscriber. Hi Joe. There's no valley of stability, Jack, I'm afraid, not in the first year. I'll save that for another stream another day. So they're pushing each other away from each other, and there's no effect from the strong force. When we get really large nuclei, we can get ejected alpha particles. So unstable nuclei that are really big can eject alpha particles because they're pushing against each other. All these charged things are pushing against each other, and they're being pulled back in by the strong force. But everything sort of, so say if this it's arranged a strong force. Everything on this side is pushing it away, and only the things in here are pulling it into the nucleus. So things can decay by alpha decay. Alpha decay does a funny thing to our nucleus. So say we had a nucleus A Z, and then that decays, so it's a big nucleus. Big nuclei tend to decay by alpha decay. It's going to change to element Y, and our mass number is going to decrease by 4, and our proton number is going to decrease by 2. So I've got 2 protons that have left and 4 nucleons that have left, and plus 4 to alpha particle, and we're going to say there's a gamma release as well when the nucleus reshuffles. So we need to make sure that the numbers on the top on this side add up to numbers on the top on this side, and the numbers on the bottom add up to numbers on the bottom. So we've got conservation of mass, so we've got 4, and then A minus 4 equals A, and conservation of charge, we've got 2 plus Z minus 2 equals Z. So we've got conservation of mass and conservation of charge. If we have a nucleus with too many neutrons, we can get beta decay. Jason, how's it going? It's been a long time. Hope everything's going well. If we have a nucleus with too many neutrons, then a neutron can change into a proton. Neutrons are unstable. If they're in the air, just hanging about by themselves, they've got a half-life of about so that's a diameter. This is a large nucleus, chat, with a diameter of about 10 to the minus 14 meters. So if we have too many neutrons, a neutron can decay into a proton. Neutrons on their own have a half-life of about 10 minutes. They can decay spontaneously when they're on their own, but they're more stable when they're inside a nucleus. So my element X is going to decay into a different element, element Y. My atomic mass number, my mass, is going to stay the same because I've got I might be guessing a bit with this number, Jack. So if we've got too many neutrons, a neutron decays into a proton, giving us 1 extra proton, and it also stays behind as a proton. So neutrons change into a proton, so our entire mass hasn't changed, but we've got an extra proton. So then we also get a beta particle, and a beta particle is a high energy electron. So it's got -1 charge and more or less 0 mass. We also have to have an anti-electron neutrino. We can talk about this a bit more later. And they have 0 mass, 0 charge. They do a couple of things for us. They conserve lepton number. So we've made what's called a lepton. But we can't create leptons without creating anti-leptons. We have to conserve lepton number. In the same way we have to conserve charge, we have to conserve lepton number. So we have to have an anti-lepton to cancel out the lepton. We'll talk about that a bit more later. We may also have a gamma to get rid of any excess energy, but it might be that the energy is all used up by these two. So my beta particle can have a range of energies, which is a little bit weird. So what we'd expect when this decay happens, so a neutron changes into a proton, and there's a mass difference of something like 0.003 times 10 to the power minus 27 kilograms. That changes into energy and mass. So we've got the mass of the electron and some leftover energy, and that leftover energy should be the kinetic energy of the beta particle. But when they measured it, the beta particles had a huge range of energies, and that didn't make sense. So they postulated back in the day that there must be something else sharing the kinetic energy. So if there was no gamma, then there must be something else sharing the energy with the beta particles, and it must have been neutral because charge is already conserved, It must have been quite light. So it's very small, like an electron. It's a light neutral particle called a neutrino. If we call it just a neutrino, then it's probably an electron neutrino. There are other types of neutrinos that we're going to talk about a little bit later, but if it's just a neutrino, then we'll call it an electron neutrino. Oh, so there we go. We talked about the need for the neutrino, and we've talked about the existence of the neutrino being hypothesized to account for conservation of energy and beta decay. Now, neutrinos are really, really, really tricky to measure. We can do it now, but it's not very easy. We have huge detectors. Cool. So that's stable and unstable nuclei. You need to remember the strong nuclear force is repulsive at distances smaller than 0.5 femtometers, and attractive at distances up until 3 femtometers. After 3 femtometers, we've got no effect from the strong force. The other force in the nucleus is the electrostatic force or electromagnetic force. Okay, particles, antiparticles, and photons. So for every type of particle, let's say a proton, it has a corresponding antiparticle, which is an antiproton. And this bar means it's an antiparticle. So we could have an electron bar, a neutron, and a neutron bar. So these are antiparticles. Every particle has an antiparticle. Some particles, like photons, have their own antiparticle. So they don't have a bar on top. So some particles, like photons, are their own antiparticles, which is a bit weird. Photons probably the only one you're going to need to know about. So protons, antiprotons, electrons, anti-electrons, neutrons, antineutrons. With electrons, we have an electron which is an E minus, and an E plus is called a positron. So anti-electrons get their own special name, which is cute. So masses, charge, and rest energy in mega electron volts. So if we talk about particles, proton, electron, neutron, and photon, we'll ignore photon because it doesn't have mass or charge, and it has variable energies, but it doesn't have rest energy because it never stays still. I think we've stopped the photon. Scientists at large, I'm not entirely sure how that works. So with our protons, particle and antiparticles, they have the same mass, same rest energy, but opposite charge. So protons have a +1 charge, antiprotons have a -1 charge, electrons have a -1 charge, and positrons have a +1 charge. Neutrons have 0 charge, and antineutrons have 0 charge, but they are slightly different. So a neutron's made up of 3 quarks, and an antineutron is made up of 3 antiquarks. Rest energies in mega electron volts we didn't talk about, but they are in the data book. So if we take a look at it's in here somewhere. Protons rest energy is given to you as 938.257, which is a bit mad. So protons rest energy is 938.257. That's in mega electron volts. We'll talk about the electron volt in a second. Neutron, hopefully, is in there. 939.551, 939.551 mega electron volts, and then an electron 0.510999. 0.510999 mega electron volts. So that's times 10 to the power 6 electron volts. We can see again that the proton is slightly less massive than the neutron. Yeah, photons are certainly intriguing, Jack. So we see that neutrons are slightly heavier than protons. They have slightly more rest. Neutrons have slightly more rest energy, and electrons are about 2,000 times smaller or less massive than. So if they're about 1,000, that's about half. That's about 2,000 times smaller. Which means that the rest energies of antiprotons, anti-electrons, and antineutrons are the same as these. Not negative. We don't have negative mass, and we don't have negative energy, so they are the same. Let's talk about the electron volt. So 1 electron volt is the energy gained by an electron as it passes through a potential difference of 1 volt. So if we know that 1 volt is 1 joule per coulomb, then we can calculate that energy must be potential difference multiplied by charge. So energy or work done is 1, it's going to be our charge multiplied by our voltage. So if we want to find out how many joules an electron gains, it will be 1.60 times 10 to the power minus 19 multiplied by 1 volt. So that will give us our electron volt in joules. So 1 electron volt equals 1.60 times 10 to the power minus 19 joules, which is really, really small. But the masses and the energies that we're talking about are also really small. If we're converting from mega electron volts, then we can use 1.60 times 10 to the power minus 13 joules, and that is absolutely fine. You should know that the positron, antiproton, antineutrino, antineutron and antineutrino are the antiparticles of the electron, proton, neutron and neutrino respectively. So we should add up here a neutrino and an antineutrino. They're a little bit boring. I'm going to put an E on there because we're always talking about electron neutrinos in this course. These ones are a bit weird. So neutrinos do have antiparticles, but they're not made of anything else, and they've got no charge. So photons with no charge are their own antiparticle, but neutrinos with no charge are their own antiparticle, which is very strange. But that's okay. So this is all about particles and antiparticles. Protons, antiprotons, electrons, anti-electrons, neutrons, antineutrons, neutrinos, antineutrinos. Their rest energies, so we can add on here. Oh, not that one. Anti-neutron, anti-electron. So the particle and the antiparticle have the same rest energy. We talked about the masses earlier. So the mass of an antiproton is going to be 1.673 times 10 to the power minus 27 kilograms, and an antineutron is 1.675 times 10 to the minus 27 kilograms, and our electron is 9.11 times 10 to the minus 31 kilograms, and the same for the positron. I am just going to go and blow my nose. So I think I can do this. and this. I'll be right back. I think I can also mute the sound. I'm having fun right now, Jack. Definitely. I am back. I need to go back to my drawing screen. Holy pig frill, who are you? I'm going to want to speed up a little bit, otherwise we could well be here all day. Right, I'm going to rub all this out because we want to talk about photons now. There's probably a better way to do this, but I couldn't figure out how to rub things out earlier, so I was excited when I found that out. Obviously you can just rewind this later. This will be up on my channel forever until I get too embarrassed by myself talking on the internet to take it down. I was also in another video earlier this week promoting Exeter College, of course. Very exciting video promoting the Maths and Science faculty. So we need to talk about the photon model of electromagnetic radiation. So you know about electromagnetic radiation, it's a transverse wave. If you want to know about transverse waves, check out the wave specification analysis. They're interesting in that they are in their electric waves and magnetic waves at 90 degrees to one another. But we're going to forget about the wave model. We're going to put it to one side. We're not going to forget about it because photons are actually waves and particles. Elliot, excellent to see you. This is going to help. This is going to sort you out. So we're going to talk about a slightly different model where a photon is a quanta of, I think that should probably be quantum energy if it's just one, a packet of energy, a very small packet of energy that is discrete and only has a certain energy. If we want to know the energy of that photon, then we can do Planck's constant h multiplied by the frequency. H is a constant, it's in your data book, 6.63 times 10 to the power minus 34 joule seconds. If you're asked about the units for Planck's constant, then you can look it up in the data book. This will give you energy in joules. There are other values that you can use for Planck's constant for energy in electron volts and things like that, but we'll stick with it in joules. And then frequency, and F is frequency in hertz. So we're going to get some really, so just looking at, can I change colour? Or can I use, hang on, boom. No, it doesn't work. Function. F4. Did that work? So if we look at this, oh yeah, different colours. Woohoo! I've got to use function. For some reason this laptop doesn't have F buttons. It has other weird things where the F buttons should be, and you have to press function to get them up. Anyway, if we look at 10 to the power minus 34, we're going to get some really small energies, even though so gamma photons can have frequencies of something like 10 to the power 12 hertz or higher or lower. It changes depending on the type of wave. So we know we've got different types of wave. If we talk about visible light just for a second, and we're going to use a slightly broad, in fact I think it's a little bit narrow, but easy to remember, range of wavelengths, 400 nanometers to 700 nanometers. If we remember that longer wavelengths have higher frequencies, and shorter longer wavelengths have lower frequencies, and shorter wavelengths have higher frequencies. We can say that things with a shorter wavelength have higher energy, and things with a longer wavelength have lower energy. So red photons have less energy than blue photons. If we want to change from using frequency in our energy equation to wavelength, we have to introduce wave speed, which for us, for photons, it's going to be 3.00 times 10 to the power 8 meters per second. And c also equals frequency times wavelength. So what we can do is we can find frequency in terms of wavelength, and we can substitute in for frequency, so then E also equals H multiplied by C and then divided by wavelength. So this is wavelength in meters, and that's the speed of light, and that's in meters per second. So then to find our energy, if we think about these units, energy is in joules, which is joule seconds, meter seconds to the -1, meters to the power -1. That one cancels with that one cancels with that one. And we just get left with joules. So we can find the energy of a photon by E equals Planck's constant, 6.63 times 10 to the power -34, multiplied by frequency in hertz, or we can find it by Planck's constant multiplied by the speed of light, all divided by wavelength. And C is always going to be the speed of light, because we're talking about photons. It's good to see for topic 2, so first years do not have to use E equals mc squared. Nope. Second years do, and that's in the nuclear topic, but it could well find its way into other topics as well, because in your paper, in your paper 1 you won't need to know about E equals mc squared, but in paper 2 for the second years, you're going to get assessed on all the second year stuff apart from circular motion, which you've already done in paper 1. But it is going to be synoptic as well, so you can have, it could be anything. You need to know about annihilation and pair production. It's kind of a cool word. Annihilation is when a particle and an antiparticle meet, and all of their energy is turned into 2 photons. It's like an explosion, except not an explosion, that's different. We'll get rid of that. So they annihilate, all of their mass turns into energy. So let's talk about, so we're not using E equals mc squared, so the energy of each photon is going to be so we're going to get 2 energies, and it's going to be the rest mass energy plus the kinetic energy of those the particle and the antiparticle. So each one has some rest mass energy, which is going to be given to you in the paper, and then they also have some kinetic energy, so you can add those up, and that's going to equal 2 lots of HF. So this one's given you from the data book. Maybe it will be an electron and a positron, so it'll be 0.510999 times 2 plus whatever the kinetic energy they give you of the electron volts is. The kinetic energy of the electrons is. So they collide, they annihilate, they make 2 photons going in opposite directions. So the momenta of these 2 particles cancels, and then you get equal and opposite momentum for each of the photons. So what we can do, well, we could say we get 2, if they were not moving, then we get 2m0, which is our rest mass. That's wrong. Hang on. E0. So this is our rest energy. So 2 lots of our rest energy of our particles, if they're not moving, it's going to equal 2 lots of photon energy, and they cancel out the 2's. So we get the rest energy of one of the particles equals the energy of one of the photons. That's annihilation. In pair production, one photon splits into 2 particles. Now we have to make sure that our particles are in particle-antiparticle pair. It's most likely to be an electron and a positron because they are the smallest and lightest. So our smallest and lightest particles are likely to be made from high energy photons. These 2 are going to go away, and they're more than likely to collide with each other again. They're attracted to each other. Depends how much energy they've got in the form of kinetic energy, which will be the leftover energy after the energy of our photon. Hello, the boss cat. Who's the boss cat? So in this case, we've got the energy of the photon HF, and it's going to have enough energy to make 2 lots. Oh, Max, back again. 2 lots of the rest energy of these particles. It's always the same people, you know, it's always the same people. Just the cool kids that watch these streams, I'm telling you. Oh, yes, dog. 7 people watching. Oh. Up and down and up and down. Bless you. Yeah, so the energy of one photon makes the rest energy of 2 particles, and that can be if you have HF, that will give you that in joules. So you'll need to convert that to mega electron volts. So if you have, if it says the positron and electron with so much kinetic energy, so we could have plus some kinetic energy, but maybe not, are made in pair production. What's the energy of the photon? So you get 2 times the rest mass converted into joules, plus the kinetic energy in joules gives you the energy of the photon. I think we're at the bottom of the page. I don't know. Oh. Particle interactions. So we've got 4 fundamental forces. Gravity, which we're not worried about until the 2nd year, apart from in the mechanics topic, and we only really want to know about the acceleration due to gravity. The electromagnetic force, the weak nuclear force, and the strong nuclear force. The strong nuclear force may be referred to as a strong interaction. So they might ask you about weak interactions and strong interactions. I'm not sure why they only said strong, but it could be weak interaction as well. Gravity is the weakest, which is ridiculous because this one's called the weak force. The electromagnetic force is fairly strong and is inverse square. Weak nuclear force is very, very, very short range. And I should know what the range is. Let's have a look. Dog, what are you doing? About 10 to the minus 18 meters. Whoa. So hyperphysics says the weak force has a range of 10 to the minus 18 meters. So by weak, they mean it. I think I should show you my dog. She's going bonkers. This is my dog. I think you can see. Now she's barking. Dog. You're live on the internet, Minnie. Say something. No? Okay. I don't know why you're beating me up. I know. What is wrong? You've been out, you've got food. Chew your bones. Need to go out for a walk, don't we? It's all snowy though. Go and lie down. She is a pain in the neck dog. But she's very lovely. You're not wrong. Oh, with 2 subscribers. Hang on just one moment. Oh, I can't see. 100 subscribers! Woo! That's very exciting. I don't know. I should probably be doing particles. Are we back? Can you see? You can always see. Go under here. I'll put you outside in the snow. Right, so we're talking about the strong and the weak force, gravitational force and electromagnetic force. Electromagnetic force happens between charged particles. Gravity happens between particles with mass. Weak nuclear force happens between more or less all particles, and the strong nuclear force happens between baryons, which we don't know yet, but that's okay. We'll figure it out later. Concept of exchange particles. So if I've got 2 particles that are charged, say they're positive, and they come together, then they can chuck a photon at each other. They go in like this, they're coming towards each other, chuck a photon across, and they bounce away from each other like this. That's the nature of an interaction which is electromagnetic. I know, woo, it's taken me like a year and a half to get 100 subs, but that's amazing. So these positive particles come together, they exchange a photon, which changes their momentum, and they move apart. So we're going to call these, what are we going to call these? Exchange particles. So for our strong force, in fact for our strong nuclear force, it's pions. For our weak force, it's W plus, W minus, and well, Z0 as well, bosons, but the Z0 will not be tested. The strong force is actually mediated by gluons, but we don't care about gluons. So gluons are what hold quarks together inside nucleons, baryons. Gravitons, so for gravity we have gravitons, which are hypothesized and not measured, and then for the electromagnetic force we have photons, which are gammas. So knowledge of the gluon, the Z0 and the graviton will not be tested. Just grab that out. So we need to know about photons, W plus, W minus, pions, and that's it. for our exchange particles. We haven't got any exchange diagrams. Why are you attacking me? We haven't got any exchange diagrams which involve pions. So you just need to know that the strong nuclear force is mediated by pions. I'm kind of glossing over this a little bit, just with what you need to know. If you want to talk about the nature of these forces, there's an excellent series of SciShow of 4 videos, one for each of the fundamental forces: the strong force, the weak force, the gravitational force, and the electromagnetic force. For our electromagnetic force, they are the exchange particle. We're going to call them virtual photons instead of just photons. So we can't detect them. We can't detect photons at all in exchanges, but we kind of know they're there. The weak interaction is limited to beta minus, beta plus decay, electron capture, and electron-proton collisions. W plus and W minus is the exchange particles. So we need to know. We need to draw diagrams for these. So we have, these are called Feynman diagrams, and I'm going to do this if I can do it without getting my elbow bitten off. I'm going to feed the dog. 1 second. You want to eat? You actually want to just go and play with snack? Is that right? Adrian! I think the dog is going stir crazy because she's locked up in the house. Oh, Adrian and Max, thank you for the t-shirt. It's a fave. Right, back to the drawing window. Nothing new there, Jack. Adrian being late. Actually, that's not true, is it? I'm normally more late because Adrian watches me go to change and then goes upstairs then. Not watches me change, that's weird. Right, we need to talk about these simple diagrams to represent the above reactions or interactions. So the first one I want to talk about, it's gonna look like this. We're gonna have an axis here and an axis here. Once I remember what those axes are, I'll put them in. So for our diagrams, at every single vertex, which is a joining of lines, we have 2 arrows and a wiggly. So in this case, if we have, let's say, an electron, they come together in space, so this is space. This is time. So they come together in space, they're all going upwards in time, they don't change their nature. So an electromagnetic interaction, so an EM interaction, they don't change nature, they exchange a virtual photon and they change momentum and they bounce away from each other. So the exchange particle and electromagnetic interactions are virtual photons, like we talked about up here. Electrons repel, we know that from physics, so like charges repel. And the reason we're saying now in particle physics is because there's an exchange of particles. So the exchange particles, a photon goes from here to here, and then they change momentum and repel. Oh, I've got loads of space. That's amazing. Oh, we need to go up a little bit, don't we? Because we need to know which diagrams we're drawing. So our weak interaction is limited to beta minus and beta plus decay. So we'll do beta minus first, because that's our more common decay. 2 lines and a wiggly. Going to 2 more lines. Two lines and a wiggly going to 2 more lines. We have to have an arrow denoting the direction of travel of the particles. So in beta minus decay, a neutron changes to a proton. We also have to conserve charge at each of our 2 arrow and wiggly slots. So a 0 charge particle changes into a positive particle and a negative particle, and again we have to conserve charge here, so a negative is going to go to a negative plus an electron neutrino, but actually it's an anti-electron neutrino because we have to make pairs of particles and antiparticles. We can't just make particles, that would ruin the universe. So this is a weak interaction involving the exchange particle, the W minus boson. So it's a decay of a neutron into a proton. For beta plus decay, my amazing writing, the diagram looks the same. Put arrows on all of these. I'm missing. It's not easy to use one of these little graphic tablets things. So a proton changes into a neutron. This is much less likely. The exchange for a W plus, a positron comes off, and a regular electron neutrino. Oof. So we've got a proton hanging out, turns into a neutron. It's got too much energy. A W plus comes out, so we've gone from positive in to positive out and 0 charge out. We've gone from positive in to positive out and 0 charge out. So we're conserving charge at each one of these vertices. Electron capture and electron-proton collisions. So electron capture, so these are going to look the same. Electron capture is when an inner shell electron is captured by a proton in the nucleus, changing that proton into a neutron. An electron-proton collision would be the same thing, except when they're in free space. So we have a proton coming in and an electron coming in. Notice that every time this right hand side for me is higher than the left hand side, and that's because I like reading them left to right, and everything has to go up in time. So if my particle is travelling to the right, it's going up in time. So I have a proton, it collides with an electron, they're coming together. So either from an inner shell of an atom, which would be electron capture, or from a collision in free space, then my proton is going to change into a neutron, and my electron is going to change into a neutrino. So we get plus and minus going in, and 0 charge coming out. So that's electron capture. They like to ask about electron capture because then they can give you marks for saying that it's an inner shell electron. What does it mean to go up in time? It means we're going forwards in time. So if you look at this diagram here, the gradient of all my lines has to be positive in the direction that they're going. So this is a positive gradient, this has a positive gradient but in that direction, so it's going up on the time axis. If I have a particle going this way, then that represents it going backwards in time. I forgot the boson. I did forget the boson. Hang on, Jack, I had a question. So we can't have things going backwards in time in this course. So here we have an interaction. We're going from positive to a vertices here, so we have to have a positive thing coming out. Greetings. We have to have a positive thing coming out, so that's going to be a W plus because it's a weak interaction. If there is a neutrino involved, it's a weak interaction. So 1, 2, 3 decays, all weak interactions. There are no diagrams you need to learn for strong interactions. You'll need to know those kind of interactions, or how to identify those kind of interactions using decay equations. And then we have one diagram for electromagnetic interactions. Oh, that's the bottom of the page. I'd love to say that that was the end, but it's not. There's loads more. Is this easier if I... Is this... No, it's not easier if I scroll. Time travel confirmed. No, unfortunately not. But they just say that antiparticles travel backwards in time. Just not on our course. Right. This part of the spec is essentially a list of things that you need to know. We have hadrons, which are subject to the strong force or the strong interaction. Two kinds of hadrons, baryons and mesons. So these mesons are quark-antiquark pair, and the baryons are either quark, 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 or antiquark, antiquark, antiquark. Baryons that we know of are the proton, neutron, or baryons that we're going to be tested on, should I say, and then we have antibaryons as well. So let's go comma that one, comma that one, and then we have mesons. We have pions and kaons. Now pions are not strange. So pions can be up, anti-down. That would be plus 2/3. That would be a pi plus. A pi minus would be anti-up, down, and our pi zeros are pairs of particles and antiparticles. Now these exist, but only for short amounts of time because they will annihilate. I'm talking about quarks as if you know what they are. They'll come up in a minute. So hadrons are subject to the strong force. They're made of baryons and mesons. Protons, antiprotons, neutrons, antineutrons are baryons. Pions and kaons, pi mesons and k mesons, are mesons, and they're made of quark antiquark pairs. Kaons are strange, so we can have k. I think. Oh, I'm going to lose track of these. So we have up, and then anti-strange would be positive. K minus would be anti-up strange. K0 could be down, anti-strange, or anti-down strange. In my head, I'm just thinking about the diagrams in the textbook. Just to clarify, Elliot, we have not done this in our lessons yet. No. But this is for future reference. My tutor group haven't done any of particles yet. They're still finishing electricity. And today is not going to help. I know it's bad, but I was hoping for not a snow day today. Not a snow day. So, now we know about hadrons, which are baryons and mesons. We can introduce quantum numbers. Quantum numbers are a set of numbers which have to be conserved mostly. But they appear to be just randomly assigned numbers. So baryons have a baryon number of +1. Each quark has a baryon number of 1/3. Mesons have a baryon number of 0. So baryons have a baryon number. Antibaryons have a negative baryon number. Mesons, leptons, anything else does not have a baryon number. And baryon number must be conserved. Baryon number must be conserved. I need to take the dog out. She's going crazy. I am going to be right back. I'm back. The dog is in the other room because she's a pain. I don't know who that is. Is that Stashu? So we've introduced quantum numbers. Baryons have a baryon number, which is an example of a quantum number, and it must be conserved. +1, -1, +1 for a baryon, -1 for an antibaryon, and 0 for mesons. The only stable baryon is the proton. All others will eventually decay into the proton. Pions is an exchange particle for a strong force, so we talked about that. We mentioned that in the last section, but these pions are exchange particle for the strong force, but you're not going to be tested on the diagrams for those. Leptons. So we've got, in our different classes of particles, we've got hadrons, we've got leptons. Oh, hang on. We haven't got to strangeness yet. Crikey. No, strangeness is only conserved in strong interactions. No, hang on. Rewind. Strangeness can always be conserved, but may not be conserved in weak interactions, chaps. Let's not get ahead of ourselves now. So we've got electrons, muons, and neutrinos. Now, neutrinos are assigned to the respective leptons. So we've also got, so muon is a mu minus, we've also got anti-leptons. Muons are heavy electrons. They have the same properties as electrons, except they're much heavier. Positrons and anti-muons. Similar business. Neutrinos are also leptons. So leptons are fundamental. There's nothing smaller than the lepton. Baryons and mesons are not fundamental. They're made up of quarks, which are fundamental. Electron and muon types only, and their antiparticles. So we do need to know that there are electron neutrinos and muon neutrinos. Both exist. Every time you do one of your decay diagrams, though, it will be an electron neutrino or an anti-electron neutrino, depending on the decay. Kaon is a particle that can decay into pion, so kaons can go to pions. Lepton number is another quantum number. So leptons have if it's a lepton, it has a lepton number +1, and then anti-leptons have a lepton number of -1, and this has to be conserved in every interaction. So we talked about earlier beta decay, so a neutron changes into a proton, so we've got 0 leptons on that side of the decay. And then on the other side we've got an electron and an anti-electron neutrino. So a lepton with +1 lepton number is created, so an anti-lepton must be created at the same time. So these rules, these quantum numbers, these are empirical rules. So some decays that should happen never happen. So we must conserve these quantum numbers. So lepton number is a quantum number. Ravenous squirrel, you probably have missed a lot, but you can always go back. Not a problem. Conservation down here. Muon as a particle that decays into an electron. So muons as heavy electrons are leptons, and they can decay into electrons, and there should be a decay equation for that, whether you need to know it or not. I wonder. Oops. Nope. So Wikipedia says that we have this isn't one. Oh no, I've broken it. So Wikipedia says it's not a decay that you need to know, but a muon, mu minus, via a weak interaction can decay into a muon neutrino and an electron and an electron neutrino. So we've got it's going to have to be an anti, isn't it? Because we've created a lepton out of nowhere. So we've got, on this side we've got a lepton number of, so our decay could look like muon decays into muon neutrino plus electron plus anti-electron neutrino. So we've got a lepton number on this side of +1, we've got a +1 for that one, a +1 for that one, and a -1 for that one. So those two cancel, giving me a lepton number of +1 before the interaction and a lepton number of +1 after the interaction. So that's how you could describe the decay of a muon into an electron. Strange particles. Any particle which contains a strange quark has what's called strangeness. So a strange particle, strangely, has a strangeness of -1, and an anti-strange particle has a strangeness of +1. So particles try to decay to become lighter. Yes, which is why neutrons decay into protons quite readily. So beta decay or beta minus decay is quite common, and then beta plus decay is less common. So that's a proton getting heavier to become a neutron, so not very common. Muons decaying into electrons is quite common, and we can probably say that muons have a half-life of, it's not very long, 2.2 microseconds. Whoa. And there's a whole crazy thing about why muons reach detectors, even though they shouldn't, because of the way in relativity time slows down. So time slows down for them to reach the surface of the Earth. Anyway, we were talking about strangeness. So strangeness is strange in that a strange particle has -1 strangeness and an anti-strange particle has a +1 strangeness. Strange particles are particles that produce through the strong interaction and decay through the weak. So strange particles are produced in strong interactions, but always produced in particle-antiparticle pairs, and decay is a weak interaction. So we can have in a weak interaction we can have a change of strangeness. So we can either have 0, +1 or -1, because we can create because we can get rid of strange particles or strange quarks. In in strong interactions, we always have to create them in pairs so that we have to conserve strangeness. So every time we produce strange particles in strong interactions, we make a strange particle and an anti-strange particle. When strange particles decay, they don't have to decay in weak interactions, but they could increase or decrease lepton number by +1 or -1, which would indicate a +1 would be a strange quark decaying, and then a -1 would be an anti-strange quark decaying. That's the wrong way around, isn't it? So if an anti-strange quark went from +1 to 0, so if an anti-strange quark decayed in a weak interaction, there was a strangeness change of -1. And then if a strange quark with a strangeness of -1 decayed, you'd get a change in strangeness of +1. Change in strangeness. That's a lot to say. It's a mouthful. We'll get back to this in a bit. So you need to appreciate that particle physics relies on the collaborative efforts of large teams of scientists and engineers to validate new knowledge. Projects like CERN, the Large Hadron Collider, which is always in the news, discovering new particles. I want to say most recently, but there's definitely more things they've done since then, but the Higgs boson was a big one for them. Okay. Properties of quarks and antiquarks. So we've been talking about quarks quite a lot, and we have to talk about an up quark, a down quark, and a strange quark. So their symbols are up, down, strange. They each have an antiparticle. Up quarks have a charge of +2/3. So let's talk about charge in this column here. Down is -1/3, and strange is -1/3. Baryon number +1/3, +1/3, +1/3, and strangeness 0, 0, -1. So if you want antiparticles of all of these, you have to flip all of these quantum numbers. There are more quarks. There are 6. There's up, down, strange, charm, top and bottom. So charm, top and bottom are heavy, and we're not really too worried about those. We're only talking about up, down, strange quarks. Again, there's another great song by the chap that does SciShow, and I can't remember his name. It's called Up, Down, Strange, Charm, or the Quark Song or something. It's very good. Go and check it out. We love SciShow. He talks really fast, but that's okay. So for protons are not fundamental. They're made of an up, and a down quark. Neutrons, again not fundamental. They are up, down, down, and then the antiparticles for an antiproton and antineutron just contain the antiquarks. So if you flip all of the charges, so up will become -2/3, and that will become that's wrong. That is wrong. I'll just change this one a second to an anti-up. So -2/3, -2/3, +1/3 equals -1, and +2/3, +2/3, -1/3 equals 1. That gives us our charges. Are we going to do all this in lessons? Yes, Jonah, we are going to do all this in lessons, and you can always come back and revise on here. We talked earlier about particles which contain strange quarks. The only ones that you're going to be tested on are kaons. Are the only strange particles you're going to be tested on, or have to remember. You might be tested on others, but they'll give you details which will enable you to figure those out. George! Hang on a second. You don't need to know this stuff. You know this stuff. Good to see you though, or at least, you know, not see you. You know what I mean. Hope it's all going well up in Lancaster. It was Lancaster, right? Lots of astrophysics. We just started, well, soon to be starting astrophysics with the second years. Anyway, the decay of the neutron should be known. Ooh. The decay of the neutron is Fabby. So we can talk about the decay of the neutron in a slightly different way. We can do our Feynman diagrams, our interaction diagrams, in a slightly different way, like this. So we can break these down into quarks. So when a neutron decays into a proton, it goes from up, down, down to up, down, up. So that down quark, which is slightly heavier than an up quark, decays by emitting a W minus boson. So it's going from this is going from minus 1/3 charge to plus 1/3, plus 2/3 charge. That doesn't make any sense. Down changes to down. Yeah, so that's gaining 1, so this must be minus 1, that's right. And then that's going to change into an electron again, and an anti-electron neutrino. Fabby dabby. So that's another way to talk about the decay of a neutron. So from up, down, down, to up, down, up. So there's actually the down quark which decays into an up quark when a neutron changes into a proton. I don't think I've ever read this part of the spec. That's pretty bad, isn't it? Change of quark character in beta minus and beta plus decay. Oh, I just did that. So in beta minus decay, a down quark changes to an up quark. Beta plus decay, and up quark changes into a down quark. So that changes the quarks. So that is a weak interaction with no change in strangeness. Application of the conservation laws for charge, baryon number, lepton number, and strangeness to particle interactions. Necessary data provided. So energy and momentum are always conserved in interactions, and mass as well. Mass, energy, energy, mass, energy. It's all the same thing, more or less. Oh, this is a little bit tedious. So if we talk about a Q, B, L, S. Let's talk about let's talk about beta plus decay. So a proton changes to a neutron plus a positron plus an electron neutrino. So we have to talk about our quantum number, or our different quantum numbers, and we have to conserve certain ones. So our strangeness is actually going to be 0 everywhere, so it's not too big of a worry. My charge goes from plus 1 to 0, plus 1, plus 0. So we've got 1 on this side, 1 on this side. That's fine. Our baryon number for a proton is plus 1, for a neutron is plus 1. For any leptons, they've got a baryon number of 0, so we've got 1 on this side and 1 on this side. On this side of the equation, we've got 0 for our lepton number, 0 for the lepton number because these are baryons. Then we've got minus 1 because that's an anti-lepton, plus 1, that is a lepton. So our positron is an anti-lepton, and our neutrino, our electron neutrino, is a lepton. So we've got minus 1 plus 1 is 0, 0, and then 0 on this side, which is lovely. My suggestion would be to go through as many past papers as you can and try out those questions, because they are really tricky. And if you've got any questions, ask me. I've got a big sheet of them. We'll do when we get to it in class. No. Photoelectric effect. So, if we have photons, well, I can do different colours for this as well. So let's have a green photon and a red photon. Incident on the surface of a metal. And inside my metal, we've talked about, we've got these positive ions in a lattice, all held together by electrons. We have this sea of delocalized electrons. Sam, that whole crew is back together, more or less. Thank you for my congrats on 100 subs. I'm very pleased. Very pleased. So these are two photons with different energies. The red photon has less energy than the green photon. Now, we know that the energy of the photons equals HF. If the energy is big enough, it's possible to knock an electron off the surface of the metal. So F0 gives us the minimum energy required to remove an electron from the surface of the metal, and that is the definition of work function. So the work function of a metal is the minimum energy required to remove an electron from the surface of a metal. So in this case, my green photon has got enough energy to remove an electron from the surface, and my red photon does not have enough energy to remove an electron from the surface. WhatsApp's going crazy. If I were to have a blue photon come down and collide with this electron, then it is possible that this electron can pop off, even though that electron isn't on the surface of the metal. So this time the energy required is going to be, in fact, let's do it a different way. So this time we have my work function plus some other energy to get it out of the surface of the metal. So if I use the work function, I can find that when my photon collides with an electron, I can get some maximum kinetic energy, and that's going to be the energy of the photon minus the work done in removing the electron from the surface of the metal. So this is a maximum, because if it's not at the surface of the metal, the energy required to leave the metal is greater than the work function. So my photons we're treating as particles, and that particle collides with an electron with a particle and is absorbed. The electron then has that much extra energy. If that much extra energy is enough, it can leave the surface of the metal. If it's not enough, the electron stays in the metal and might re-radiate a photon later. If it is enough, then the leftover energy from the photon goes into the kinetic energy of the electron that's leaving. If the electron isn't at the surface, it takes more energy to get the electron out, so then you get less kinetic energy of the electron, which is why in this equation we have kinetic energy, which is a maximum. So the way you'll get it in your data book is the energy of the photon is going to be equal to the energy that it takes to remove the electron plus the energy the electron gains as kinetic energy, or the maximum energy the electron gains. Stopping potential, even though it asks you not to worry about stopping potential, if I were to put a negative surface up here and a positive surface up here, my electron might leave and then come back. And using this method, if I get my electron to come all the way up to here, and I know this potential difference, I can calculate the energy of the electron. So again, we're back to this equation which people think, oh, I won't need to use it in this topic. Energy is charge times potential difference. Hi Roberta. Yeah, you don't need to stay for the whole thing. It'll be up on YouTube afterwards, so you can skip through and go to all the different bits. If you want to come back to it after we've done the lessons on it, then that's fine. Nice to see ya. The photoelectric effect is a bit weird, and we'll do a whole lesson on it in class. This is good for revision though. So, collision of electrons with atoms. So if I have where should we start with this? So the electron volt we did earlier, and converting electron volt into joules, 1 electron volt is 1.60 times 10 to the power minus 19 joules. I don't know why I did a little thing on the 9. But ionization and excitation, understanding in the fluorescent tube. Fluorescent tube questions are really, really annoying. So let's do both of these together. Let's talk about energy levels in atoms. So if I have an atom, and we talked earlier about shells, I'm going to make a hash of making the maybe I'm not. Hang on, let's see if I can. No, I don't want that one. Yeah, I do. Yay! Alright, let's put that one over there. And I don't have to remember all of. I don't have to remember all the energy levels. So we talked about atoms earlier, and in this case, this is a model of a hydrogen atom. So we can draw circles that our chemists would call shells, or maybe even orbitals now, and we have an electron which sits in one of these shells, and if my electron gains energy, it can jump up to the next one, and there are loads more outside of this. So the line that I've drawn here from our ground state, so n equals 1, we're going to call that our ground state, and that's where our electrons want to be. They want to be as close as possible to the positive nucleus. The arrow that I drew represents this transition here from the ground state to n equals 2. Now we've got these energies, we've got all these energies down the side, and they're all negative. So when my electron is at infinity, at the top here, this is called ionization. And ionization in this context is where my electron leaves the atom. So it leaves my atom charged, it becomes an ion, ionization. In these other cases where I have transitions between other energy levels, this is called excitation. And there are two methods for excitation. It could be a photon, which interacts with an electron and raises it up an energy level, which is a little bit different to up here. So these electrons don't have energy levels in the same way. They are delocalized. They're not stuck to an atom or an ion. They are free to move about. That's why metals are good conductors of heat and of electricity. So these electrons have energy levels because they're stuck, they're bound to atoms. So it could be a photon that comes collides with the electron, is absorbed, so we get one-to-one interactions between photons and electrons, is absorbed and then moves up to another energy level. Or it could be another electron which comes in and collides with an electron. So some of the kinetic energy of this gets transferred to the energy of the atom, the electron which is bound to the atom. There's only one method of what we're going to call de-excitation. And that is the emission of a photon. I have done 1 volt is 1 joule per coulomb this year, yes. This is a different story for a different time. If you're around, you should pop in, George. So de-excitation releases a photon, and our line spectra, which I'll find a picture of in a second, is evidence for these discrete transitions. So you can only get these transitions of electrons in atoms. So in hydrogen you can only get a difference of 10.19 electron volts, or I don't know, a bit more, 7. I can't do it in my head. And this one's 0.76 electron volts. Could you quickly go back over the second method of excitation? Yeah, no worries. So we only have these transitions, so we only get these energies. So for excitation we've got 2 methods. We've got a photon. Not a stupid question at all. It's not actually a negative energy, right? Let's do that one first and then we'll do jacks. So when the electron is free, it has 0 energy of this bound state. If it gets bound to the atom, then the electric potential energy we call negative, because we have to put in energy to get it back to 0. So the way we define it, we say that at infinity the electric potential energy is 0, and then as we get closer the electric potential energy increases. It's the same for gravitational potential energy, except in this case we can only have discrete jumps. So when I'm way down here, I have to put in 13.59 electron volts in order to get way back up to 0 to ionize it. So we just define being ionized as 0 energy, and as we get closer to the nucleus, we have to put in more energy to get it out. So we say that the energy is a negative, so if we plus energy, we can get back up to 0. So my photon can come in, have a one-to-one interaction with an electron in the ground state and excite it to move up here. An electron from anywhere else can collide with this electron down here and then increase the energy of the electron. So in this case, let's say this photon must have, to undergo this transition, an energy of 10.19 electron volts. It has to have that. It can't have anything different. However, this one can have an energy of anything it likes, really. It will impart 10.19 electron volts. So if we start with a kinetic energy, that's going to equal 10.19 plus the new kinetic energy of that electron. So this is the initial kinetic energy of the electron that's coming in from somewhere else. It collides with this electron here. That electron undergoes this transition of 10.19 electron volts, and my original electron has lost some kinetic energy and has some new kinetic energy, which is 10.19 electron volts less than its original kinetic energy. So the question is, one of the favourite questions is, how many possible transitions have I got here? So we can draw these on. Let's go. Oh, wait, no. Let's go down from the top. So we can go from 0 to minus 0.54, 0 to 0.85, 0 to minus 1.51, 0 to minus 3.4, and 0 to minus 13.59. So from this state up here, when our electron gets bound, 1, 2, 3, 4, 5 possible transitions. Sure, a postman. And then if we go from here down, we get 4 possible transitions. From here down, we get 1, 2, 3 possible transitions. From here down, we've only got 2. From here down, we've only got 1 possible transition. So we've got 5, 10, 15 possible transitions from a free electron into the ground state or any other state of a hydrogen atom. With our photon, the photon has to have discrete energy because there are only specific jumps it can make in energy. So if I have, if I start at 0.85 and I end up at 3.4, so I get a transition that looks a bit like this. Then my E1 is minus 0.85, and I get minus E2, which is 3.4, and that's going to give me 2.55 electron volts, and that's positive. That's energy leaving. That's energy leaving the atom. So my photon comes off like this. In questions, energy levels may be correct in joules or electron volts. These are in electron volts. Just be careful you check the scale. I've ignored ionization and excitation in the fluorescent tube. So in a fluorescent tube, we have mercury, which is vaporized when we put an electric current across the tube, and then ionized. And then those mercury ions collide with the electrons going the other way, exciting the mercury ions and releasing ultraviolet photons. Those ultraviolet photons collide with a phosphorus coating. The phosphorus gets excited, and then as the electrons jump back down in the phosphorus atom, we get a range of photons which to our eyes all adds up to white light. So in phosphorescent coatings we can get white light, and we'll do that one in more detail in class. Make some lovely detailed notes which are a little bit boring. Ooh, it's up here somewhere. This is our last section, which is good because it's a little bit confusing. How long have we been going for now? Oh, this is going to be our longest stream ever. Oof, it's quite a big topic. So, wave-particle duality. So we said earlier on when we were talking about photons that photons are a model for light, and our other model for light is wave. So it can be a wave and it can be a particle. In fact, all particles also have wave-like properties, and all waves have particle-like properties. So you should know that electron diffraction suggests particles possess wave properties. Okay, let's have a look at that. So we know that if we pass a wave through a gap, it spreads out like this. And we end up with a single slit diffraction pattern, which looks like this. And we put waves through different combinations of slits so we can get different diffraction patterns. So what they did is they put electrons through a thin, and we'll do this in class, so we put electrons incident on a thin graphite target. Now graphite has a hexagonal structure, and so it's got some holes that you can send electrons through. So you'd expect some dots to appear on a screen behind. So if that's a screen behind, you'd expect some dots to appear. What we actually see is a diffraction pattern from the electrons. So this experiment tells us that if we pass electrons, which are particles, through small holes, that the electrons diffract. Now this doesn't work if electrons are particles. So we know that electrons possess particle properties and wave properties. We know that electrons possess particle properties because we can collide them with things and we can treat them as little balls normally, but they also possess wave-like properties. Our photoelectric effect, so earlier on when we had electrons on the surface of the atoms and photons coming in, because we get this one-to-one interaction between electrons and photons to pop them off, we know that photons must behave like particles. So we don't get a wave-like behaviour where if we had energy incident on the surface for a long enough time, eventually the electrons would start to come off. It would heat up and electrons would start to come off. We don't see that at all. What we do see is single photon instant on electron, and if and only if it's got enough energy, it will pop an electron off. So we see instantaneous emission of electrons when they're hit with photons with enough energy, and if the surface is hit with photons with not enough energy, we never see electrons coming out when they've got light instant on, which is amazing. Details of particular methods of particle diffraction are not expected. So with particle diffraction we can also do neutron diffraction, but you don't need to do details of that, so we'll cross that one out. We don't need that one. Rubbish. So if we want to find the wavelength of a particle, the wavelength of a particle is equal to Planck's constant divided by the momentum of the particle. And momentum, as we already know from mechanics, is equal to mv. Yeah, these all need to be in SI units, meters per second, kilograms, and then that's in joule seconds, and it will come out in meters. Watch program yesterday talking about a double slit experiment with electrons. That was confusing. Yes, yes it is. And we'll watch some videos in class. Dr. Quantum is a good one. If you Google Dr. Quantum, there's lots of good quantum mechanics videos. Students should be able to explain how and why the amount of diffraction changes when the momentum of the particle is increased. So if I have an electron, it's a fixed mass, the Planck constant is a constant, but I can change the velocity. So the wavelength is actually proportional to 1 over the velocity of the electron. So if I have an electron going faster, we get a smaller wavelength, which means if I'm looking at diffraction, if I have a smaller wavelength, I get less diffraction. If I have a longer wavelength, I get more diffraction. So if I have faster electrons, my diffraction pattern changes, and I can show you this when we do it in class with the Teltron tube. So if we increase the energy of the electrons, if we make the electrons go faster by increasing the potential difference, we'll do the ins and outs of an electron gun as well. Appreciation of how knowledge and understanding of the nature of matter changes over time. So this has all happened really within the last 100 years. So the photoelectric effect was what Einstein got his Nobel Prize for in, was it 1919 or something like that, or early 1920s. And appreciation that such changes need to be evaluated through peer review, so other scientists checking and redoing their work, and validation by the scientific community. So they have to. So experiments are done, and then they get published in a journal, and then other scientists in little white coats do the experiments. It's going to be a lady scientist. They do the experiments, and then they come back and they say yes or no, And if it's yes, we do some more tests. If it's no, we do some more tests. Or we change the test, or we do something slightly different. So over time, scientific theories get built up, and the name, if I can remember the order that words go in, is a scientific method. And this is not just like what we talk about in class. This is decades, if not centuries, of people trying things, getting them wrong, fixing it, changing the experiment, and all that good stuff. I think that's the end. I'll check we haven't missed anything from the spec. Then we go on to waves, and in the waves, specification analysis is already up, and you can watch that one. So we've already got waves, we've already got electricity, because those are the ones that people found the hardest. This is the particles topic. This is the one that's probably the easiest to get marks for, but probably the hardest to get your head around. So don't worry about getting your head around it completely. What's left to do? Mechanics and materials will be the next one, I expect, and I might think about doing some second year ones. I'll try and get the mechanics and materials one up over the Easter holiday. I've been able to look at the thingy mabob over time. 100 subscribers. Woohoo! I've been able to check the chat over time, which is great, on my little phone. No worries. Don't forget to smash that like button. No, I won't say that. No, I did say that. Damn. Oh, stream health is amber. My viewers may be experiencing minor issues. I'm sorry if there's any lag. I've got children on the internet because everyone's on a snow day. It's been a pleasure, and I will see you all probably tomorrow, except George. Nice to see you. Sam, nice to see you. Cheerio. Goodbye. This is where I always remember how to forget how to stop it.